Chapter 6, Exponential and Logarithmic Functions. We'll start out with section 6.1 on the natural logarithmic and exponential functions. Now, quick reminder, exponential functions, these are functions that are in the form f of x equals b to the x, where b is greater than 0 and not equal to 1. These are functions that are known for increasing very rapidly, right? And then logarithmic functions are the inverses of exponential functions. So it might look something like this. G of x is equal to log base b of x. Okay, and we'll talk about the graphs of these in just a moment. But recall down here for base b, where b is greater than 0, not equal to 1, b of y is equal to x if and only if y equals log base b of x. So this is just asserting that the exponential function base b and the logarithmic function base b are inverses, mainly because the input y for the exponential function is the output for the logarithmic function base b, and the output of the exponential is the input for the logarithmic. All right, and this is true for any base b greater than 0, not equal to 1. One of the most important, probably the most important of all the bases of all the exponential functions is the exponential and logarithmic functions base e. So for base e, this is a very important irrational number, which is approximately 2.72 something. I forget what comes after that. I don't round it much higher than that generally. This is called Euler's number. Named after the extremely prolific mathematician Euler. For base e, we have the same type of thing going on, where we have so e to the y is equal to x if and only if y is equal to the natural log of x. Okay, and you might remember from college algebra, or if we discussed it before, the natural log ln, that's just the notation and the special name for the logarithmic function base e. Oops, let me make that more clear. Log base e of x. Okay, and it gets its special notation and it has its own place on your calculator. You should have a natural logarithm button as well as an e to the x button on your calculator. And it gets this special treatment because it is so useful. There are so many incredible applications that come out of just the logarithmic and exponential functions base e. Now, a quick note about graphs and domains. You might remember the graph of the natural logarithm looks kind of like this, and this is going to be a very rough sketch, but it has this type of shape like this. Right, so this is y equals natural log of x. Just a couple of important features to note here. We have an x-intercept at 1, 0. This is actually the case for any logarithmic function with any base. And it'll have this point E1. And the other very important feature to be aware of is we have a vertical asymptote at the line x equals 0, also known as the y-axis. And I wanted to point this out because this makes it clear, visually what the domain of the natural log is. It's going to be all real numbers strictly greater than 0. Notice that, it's never going to cross over this vertical asymptote, so the whole graph is going to be strictly to the right of the y-axis. Okay, and I wanted to point this out just because we're going to get a new sort of special integral calculus definition of the natural logarithm, or the natural log of x. And we require that x is strictly greater than 0. So the natural logarithm for a number x greater than 0 is given by this integral, the integral from 1 to x of 1 over t dt. This is very strange and very interesting, but what this tells us is that the natural logarithm of x, this is actually an area formula. It serves as an area formula. It gives us the area under the curve of y equals 1 over t from 1 up to x. Okay, so y equals 1 over t, or just to remind you, y equals 1 over x. We've seen this graph surely many times. This is one of our toolkit functions or parent function for hyperbolas. So the graph of y equals 1 over x, and forgive my very sketchy drawing, looks something like this, where we have a horizontal asymptote at the x-axis, vertical asymptote at the y-axis. Okay, so the natural logarithm gives us the area under the curve of this function, however, only to the right of the y-axis, again, because of this restriction on the domain of the natural logarithm. Okay, so really it's like the area under the curve of this right branch in the first quadrant. Okay, so there are a couple things that we have to be aware of as far as like the inputs, the possible inputs for the natural logarithm function, and understanding it in the context of this, it's serving as an area function for 1 over t. If x is greater than 1, then it's pretty straightforward, right? Like here's 1, here is x, and we're just looking at the integral from 1 to x of 1 over t. And we get this area. This is pretty intuitive. We've worked with areas under curves and using integrals to find net area. So this is straightforward. Where it gets a little bit weird is, what if x is between 0 and 1? Okay, so that would be like this picture over here. Now, if x is between 0 and 1, then x is less than 1, meaning that, looking up here at this integral and this definition, that means that the upper limit of integration is smaller. It's a smaller number than the lower limit of integration, which is kind of awkward. Oftentimes, or generally, we like to have the upper limit be the larger value. So we might rewrite it like this. Negative 1 times the integral of x to 1 of 1 over t dt. This is a property of definite integrals. If we switch the limits of integration, it introduces a negative sign. So it flips the sign of the integral. Okay, so if we do this, because x is a smaller, it's smaller than 1, we're going to end up with a negative output. Okay, so that's why, this picture, the net area is actually a negative number. It's going to be less than 0. Okay, so that covers, what we're talking about, some properties down here. If x is greater than 1, we're expecting a positive natural logarithm output. If x is less than 1, it should be negative. What if x is equal to 1? Well, if it's equal to 1, then we're just looking at the integral from 1 to 1, right? The integral from 1 to 1 of 1 over t dt. Notice that if we're looking from 1 to 1, there is no width to that area. Okay, so it might have a height, but if there's no width, the area is going to be 0. So that is why we have, if x is equal to 1, then the natural log of 1 is equal to 0. There's no area there. Notice that all of this totally cooperates with our college algebra level of understanding of this function, right? Because to the right of x equals 1, we have positive output values, right? We're above the x-axis. To the left of x equals 1, the outputs of this function are negative. They're below the x-axis. And then right here at the x-axis, where we have an output of 0, right? If we put in 1, we get out 0. Okay, so this totally works with everything we already knew about this function. It's just a new definition in terms of an integral. All right, let's keep going. So applying the fundamental theorem of calculus, we get for x is greater than or equal to 0 if we take the derivative of the natural log, because really like we're trying to work towards being able to find a derivative and apply natural logarithms to evaluating integrals. That's sort of our goal here. If we take the derivative of the natural log, we would just be taking d dx of this integral, and the derivative with respect to x simplifies with this integral. They cancel out. We're just left with 1 over x. So there is our differentiation rule for the natural log of x. We just have that d dx of natural log x is equal to 1 over x. How nice is that? Okay, what about if we wanted to take a derivative of the natural log of negative x? Okay, well, first of all, bear in mind that we can't take the natural log of negative numbers. So really, this would be if x was less than 0, right? That's the only way that this would work. But we can still find this derivative. Here's what it's going to look like. We would have to do a chain rule, right? So first, we'll take the derivative of the outer function around the inner function, and then multiply by the derivative of the inner function. So the derivative of the inner function is just the derivative of negative x, would just be negative 1. So this just equals 1 over x as well. Okay, we just have to bear in mind that the domain of natural log of negative x, the input values for that are just going to be negative infinity up to 0. Okay, so that's the derivative part. Like, we want to be able to take the derivative of the natural log. How could we use this to evaluate integrals? So this, the integral of 1 over x dx, I know this looks so simple. You know, 1 over x, this is like one of our toolkit functions. It seems like we would totally know how to integrate this. Up until this point, we haven't been able to do this. And just to demonstrate like the issue that you would have, because normally if we were going to take an integral of this with the tools we already have, we might express it like this, x to the negative 1 dx, and then we'd think, okay, we just add 1 to the exponent, right? Trying to do a power rule, add 1 to the exponent, so then we would get x to the 0, and then divide by the new exponent, and then add c. But look at this. We can't divide by 0. Okay, so maybe you've bumped into this. Of course, I would have avoided giving you problems like this up to this point, but perhaps you've stumbled upon this dilemma. We actually can't take the integral of this using the power rule. This is what we get for the value of this integral. It's the natural log of the absolute value of x plus c. Okay. So this does not work. This is what we have to use. All right, and the absolute value is there just to protect us from putting any negative values in for x. Notice that we can't evaluate this at 0 anyway, so we don't really have to worry about 0 as an input. We just have to worry about x being negative. So there it is. Now we're able to evaluate the integral of 1 over x dx. Okay, now I just want to do a little bit of review of the properties of logarithms because, you know, we're going to be working with these quite a bit, so got to make sure we know these. Again, like always, we're assuming that the base is positive and not equal to 1. And for these properties, we're going to assume that m and n are positive numbers. If we are taking the logarithm base b of m times n, this is equal to log base b of m plus log base b of n. So in other words, if we have a product inside of a logarithm like this, we can split this into 2 separate logarithms with the same base and a plus sign in the middle. Okay, so multiplication on the inside becomes addition on the outside. Similarly, if we have division on the inside of a logarithm, so log base b of m over n, this is the same as log base b of m minus log base b of n. And the last one, if we have log base b of m to the p, so we have the input being raised to some power p, we can express this as a product p times log base b of m. So we can essentially do this kind of movement. I always think of it like this. We can take that exponent and bring it out in front as a factor. And of course, we could go in both directions, right? Sometimes we'll have a sum and we'll want to sort of simplify it and express it as a single logarithm. We could also go in this direction, right? So that's actually the type of thing we're going to do in example 1 here. We want to rewrite this as a single logarithm. We have 2 natural log x plus 2 minus 3 natural log of x minus 1 plus natural log of x squared. All right, so I would like to combine these, and I have these 3 properties at my disposal. So I see the subtraction and the addition, and I'm thinking, okay, I can use these to combine to a single logarithm. But before I do that, I have to deal with these factors out in front. I see a factor of 2, I see a factor of 3. So I might rewrite those individual terms, turning those factors into exponents. So for example, this first term I could write as the natural log, let me get black ink here. I could write this as the natural log of x plus 2 squared. And I could write this as minus the natural log of x minus 1 cubed. I also could have made that plus the natural log of x minus 1 to the negative third. So I could have brought that negative sign up there as a negative exponent if I wanted. And this last natural log of x squared is okay. I can leave it as is. So now that I have it in this form where it's just, natural log, natural log, natural log, all matching bases, I can start combining using those first 2 properties, the addition and the subtraction. And we're going to work from left to right just like we do in, if we were doing PEMDAS, right, standard order of operations. I'll start by combining these first 2 terms. I can write this as the natural log of, and this is going to be a quotient here, x plus 2 squared divided by x minus 1 cubed. Okay, and I'll just do that for now. Let's deal with this last term in a second step. The last step is going to be turning this this addition of the separate logarithms into multiplication inside of a single logarithm. So final step, I'll write this as the natural log of, make sure there's plenty of room in here. I'm going to multiply by x squared, so that'll land in the numerator, right? Because it's like x squared over 1 times x plus 2 squared divided by, in the denominator, we still just have that x minus 1 cubed. So that would be our answer. That's how we would compress that expression down to a single logarithm. Okay, and this can be helpful in simplifying logarithms, like in example 2. Let's look at part A. We want to simplify this. And just a reminder, the way that we evaluate logarithms, this is a side example. If I had log base 2 of 1 over 8, how about? What would this be equal to? Well, I always have the associated exponential problem, because really what this is asking is 2 to what power is equal to 1 over 8? That's always what I think when I'm looking at this. I'm thinking the base 2 raised to what power is equal to 1 over 8? And the output of the logarithm is the exponent. So looking at this associated logarithm, or excuse me, this associated exponential equation. Okay, well, getting it to 8, 2 cubed is 8, so I think it's going to be a, some type of raised to the third power. However, it ends up in the denominator, right? And remember, to flip a fraction, like what type of exponent causes a flip of the fraction like this? What causes us to get the reciprocal? Negative exponents. So 2 to the negative third power is what gives us 1 over 8. So that's why the answer to this very simple logarithm, evaluating this logarithm, is -3. Okay, so this one worked out relatively nicely. We got an integer as our output. Looking at part A over here, I might start by trying to evaluate these two logarithms that I have. These are both log base 10. And I would be thinking, okay, for this first one, 10 to what power is equal to 2? This is not a very nice one, right? Like, I can't think of any power that I could raise 10 to that would give me 2. Like, if it was log base 10 of 100, then that would be pretty straightforward, right? Because 10 squared equals 100. But this is not a easily solvable exponential equation, right? Same goes for this one over here. 10 to what power equals 5? I don't know. So let's try and work on this a little bit. Let's simplify it, maybe rewrite it as a single logarithm, see if it gets any better. So I might start by doing log base 10 of 2 squared, right? Bringing up that 2 as a power of 2. Same thing over here. Log base 10 of 5 squared. By the way, if you don't write a base, it's assumed to be 10. Just as shorthand. Okay, and then we have log of 4 plus log of 25. And then since I have a plus sign in the middle, I could multiply those together. This is log of 4 times 25, which equals log of 100. What do you know? Total coincidence that this is the one I called out earlier as being a easier logarithm to evaluate. But here we are. Log base 10 of 100. 10 to what power gives us 100? 2. 10 squared gives us 100. Okay, so by applying these properties of logarithms, we were able to simplify this down to where we could just evaluate this by hand. All right, part B, e to the negative natural log of 5. So I have to remind you of a property of logarithms. If we ever have b to the log base b of x, we just get x. This is because b of x and log base b of x are inverses of each other. So if we take the composition of those two, they cancel each other out. All right. Similarly, if we have log base b of b to the x, same thing. This is the composition of a function with its inverse, and it just simplifies down to x. So we are nearly in this form because we have, exponential function base e, we have logarithmic function base e. We just have to deal with this negative sign right here, which I can do using properties of logarithms. I could write this as e to the natural log of 5 to the negative 1, right? Just bringing that factor of -1 up as an exponent. And now we have common bases. This is just going to cancel out. We'll be left with 5 to the negative first power, or 1 over 5. Okay, and then one more example on this page, 9 to the power of log base 3 of 8. Okay, composition of an exponential function with a logarithmic function. However, we don't have the same bases, right? This is base 9, this is base 3. So we can't do the cancellation unless we could somehow express this, rewrite this as having the same bases. Now, changing the base of a logarithm, not really something that we do. However, exponential function, I could express 9 as 3 squared, right? So 3 squared log base 3 of 8. And then we have to remember the property of exponents. If we have an exponent, 3 to some power raised to another power, what we do in that case is we multiply the exponents together. Like that. And now this kind of looks like the previous example. I could write this as 3 log base 3 of 8 squared. And now we have common bases. It just cancels out. We're just left with 8 squared, or 64. And I'll box that up. Very good. So just a little practice. None of this is calculus. This is just college algebra, practicing, reviewing some of these properties of exponents, properties, laws of logarithms. Now on page 3, let's get back into some calculus. Let's look at properties of the natural log graph from the derivative. So the domain of the natural log, we discussed this earlier, is going to be x greater than 0, right? And that is because, just to get the graph back on the page here, the graph looks like this, where we have a vertical asymptote at the y-axis. Okay. Now, since the derivative, d dx of the natural log of x is 1 over x, and this is going to be positive. This is always going to be positive because the input values x are always going to be positive. This implies that the graph of the natural log is increasing across its domain. Increasing, I'll say, for all x greater than 0, so within the domain of the function. All right, and that tracks. Looking at this graph, right, we see that this graph is strictly increasing. At no point does it start to bend down and go in that direction. It increases across its entire domain. Okay, so what about the concavity of this graph? Well, we would just find a second derivative. All right, so let's take the second derivative, so d squared, like that, natural log of x. Okay, well, we'll take the first derivative first, then we'll just want d dx of 1 over x. And derivative of this, we would do a power rule, take the derivative of x to the negative first power, and okay, derivative, so we would subtract 1 from the exponent, right, and bring down the old exponent, so we would have negative 1 times x to the negative second. This is the time in the semester when people start accidentally integrating when they mean to differentiate, right, rather than differentiating when you mean to integrate, so be careful about that. Okay, so I could write this as negative 1 over x squared, like that. Notice that this is going to be less than 0 for all x in the domain. Really for all x no matter what, because if we square x no matter what it is, that's going to make it positive, and then when we multiply it by a negative, it's going to be negative. This implies that the graph is going to have downward concavity across its entire domain. So I'll say, the graph of y equals natural log x has downward concavity for all x in the domain, right? That is all x greater than 0. Okay? And again, I believe this. Looking at the graph, knowing this graph well, it does have that sort of downward concavity across the entire graph. All right, so just making some formal observations about the behavior of the graph of the natural log of x, which we can now do since we can take derivatives of the natural log. All right, next up, we should look at some derivatives. So we want to find dy dx for the following examples. Part A, y is equal to x squared times the natural log of x. Okay, I know how to take the derivative of x squared. I now know how to take a derivative of natural log of x. What do I do if they're being multiplied together? Well, we have this thing called the product rule. Okay, so good little review opportunity. Haven't seen this in a chapter or two, so let's try this out. dy dx. The way this works is I'll take the derivative of the first factor, 2x, multiply it by the second factor, add that to the first factor times the derivative of the second factor. There it is. I might write this x squared as x squared over 1 just because I'm going to multiply those together. And simplifying this first term, I could just leave as 2x natural log of x. And x squared times 1 over x, one of those factors of x will cancel. I'll just be left with x like that. So I could leave my answer that way. If you wanted to, you could factor out an x. And then this would be 2 natural log of x plus 1. I'd be happy with either one of these answers. So there it is, just applying our new rule for the derivative of natural log to a situation that we've seen many times before. Similar thing could be said for part B, y equals natural log of the square root of x. So the square root of x is inside of the natural log function. So what do we do when we're taking a derivative of a function composed with another function? This is a chain rule. So dy dx will be, okay, derivative of the outer function around the inner function. So it would be like 1 over x, but instead of x, we have root x like that. And then we're going to multiply this by the derivative of the inner function. And derivative of square root of x is 1 over 2 root x, right? You could do a power rule, just treat it as x to the 1/2 power, and you'd see that you end up with this. And simplifying a little bit, this is 1 over 2 times root x, which just gives us x. And that looks great. That's nice and simplified. 1 over 2x is our answer here. Alrighty. So now let's try an integral. We want to take the integral, definite integral, from 0 to 3 of 2x minus 1 over x plus 1 dx. Now recall, the integral of 1 over x dx is equal to the natural log absolute value of x plus c. All right. So this one here has a bit more going on, and we also have some limits of integration to deal with. So let's see what we can do. One thing that I'm noticing about this one is, I have a denominator x plus 1. Oftentimes when we have something like this where, it's a rational expression, it does not simplify. I could break this up into a couple different terms, but that wouldn't really help. I'm thinking that this is going to be a u substitution problem, right? And I think it would make sense to do something like this. Let's try to let u equal x plus 1, right? Just let u be that denominator. So then du is going to be equal to the derivative of this, which is just 1 dx. Okay, so that's nice and simple. Du is just dx. And remember, we also have to look at our limits of integration. So I'll want to look at u of 0 and u of 3, right, just to convert those x values into u values. So if I put in 0, right, I'm just using this expression or this equation right here. It'll be 0 plus 1, so the new limit of integration is going to be 1. If I put in 3, it'll be 3 plus 1, so the upper limit is going to be 4. Okay, not too bad. Now I'm going to take that and rewrite this integral in the following way. This will be the integral from now 1 to 4 of 2x minus 1 over u du. Okay, so the substitutions were that is now u, this is now du. And this is the point at which we're normally looking at this and we're thinking, okay, is every x going to cancel out here? And notice that it doesn't. We're actually stuck with this 2x up here in the numerator. So what do we do when we're in a situation where not all of the x's cancel out? Well, we have this trick where we use this, right, just our initial definition of u. I could solve for x in this, right, and I could do that by just subtracting 1 from both sides. So u minus 1 is equal to x. Okay, so this is one of those tricky u subs where there's that extra step. So let's make that one last substitution. So now this is going to be the integral from 1 to 4 of 2 times. Now, in for x, I'm going to put u minus 1. du. Okay, so just to sort of highlight the substitutions, we did the u substitution, and we also had to do this tricky little replacing x with u minus 1. Phew, okay, kind of a tricky one, but I think we're pretty much in the clear now. Let's just try and simplify a bit. I'll distribute this 2 to these two terms. We'll get 2u minus 2 minus 1 all over u du. And simplifying a little more, I get 2u minus 3 over u du. Okay, is this better? I can't tell yet. At this point, I'm going to be able to use the technique where we split up the fraction. Remember, at the beginning of the problem, we didn't attempt to do this because if you have a sum or difference in the denominator, it tends to not be very helpful. Like it doesn't aid in any kind of simplification of this rational expression. However, now that our denominator is just a single term, we just have u in the denominator, I think it's going to work out a little better. So let's split it up. We'll get 2u over u minus 3 over u du. And I'm liking how this looks because this is just going to be 2 minus 3 over u du. And these are some antiderivatives that I can find. So going term by term, this first term of 2, remember the antiderivative is just going to be 2u, right? And the second term, okay, minus 3 times the integral or the antiderivative of 1 over u, which we now know is the natural log of u. So this is going to be 3 times the natural log of u, and we are evaluating this from 1 to 4. Okay, so I might not do every single step here, but you know, the way we do this is first we put in 4. And then subtract from that, plugging in the lower limit, which is 1, so it would just be 2 minus 3 times the natural log of 1. All right, we'd simplify down a little bit. What is the natural log of 1? So e to what power equals 1? This is 0. Anything to, the natural log base anything of 1 is always just a 0. So that actually just cancels out. What we're left with when we take this difference is 6 minus 3 times the natural log of 4. And that's it. I'll box that up. That's as simplified as we would want to get it. You know, I guess you could bring that 3 up as an exponent. You could write this as the natural log of 4 to the 3rd power, which is 64. You could do that if you wanted to. But I'm totally happy with this as my answer. All right, so this is a tricky example. We have to use that special, tricky U-sub technique. But beyond that, we are just using this new definition or this new integral that we have, natural log of x. Moving on, let's talk about the exponential function. We are wanting to work towards using this function, y equals e to the x. How can we get derivatives and integrals involving this function? So starting out with some basics, first of all, note that the natural log of e, this would just be the integral from 1 to e of 1 over t dt, or dt over t, same thing. We just end up with 1, okay? And the number e can also be defined by the following limit. The limit as h goes to 0 of 1 plus h to the 1 over h power. Okay, this is kind of the origin of this number, by some account at least. But we want to know, how can we use this in calculus, in the context of derivatives and integration? So we're going to use the natural logarithm to derive a formula for the derivative of e to the x. And here's how we're going to do it. We're going to look at this. So we know that the natural log of e to the x should be equal to x. We talked about this earlier. If you compose a logarithm base e with the function e to the x, they're inverses of each other. They cancel out. We're just left with what we had as the input. Now, what we're going to do is just take the derivative with respect to x of both sides of this equation. Okay, and on the left side, this is a chain rule, right? So we would take the derivative of the outer function around the inner function. That'll look like this: 1 over e to the x, and then multiply by the derivative of e to the x, which we don't yet know, right? So I'm just going to write d dx of e to the x, right? That's how the chain rule would work out. And then this is equal to, on the right-hand side, the derivative of x with respect to x is just 1. Okay. And now I'm just going to solve for the derivative of e to the x. So I'll multiply both sides by e to the x. And we are just left with d dx e to the x is equal to e to the x. And there it is. All right, and yet another reason why Euler's number and the natural exponential function are really interesting and special. It is its own derivative. The derivative of e to the x with respect to x is e to the x. Okay. It also turns out that the integral of e to the x dx is just e to the x, of course, plus c if we're looking at an indefinite integral. So a lot of people get nervous when we start looking at, like, okay, we want to find derivatives and integrals involving this, or maybe you've seen this pop up in your textbook or whatever, and people assume that this is going to be like something that's really challenging and, you know, a pain to work with. It is the easiest derivative to find, right? It might even be easier than the derivative of a constant, right? So yeah, let's practice working with this a little bit. Let's say, for example 5, we wanted to find the derivative of f of x equals e to the x over e to the x plus 1. Now, this is looking like a quotient. Can I simplify this? Nah, again, we have this sum in the denominator, which makes it difficult. We can't just simply break it up into a couple fractions. So I'm thinking I'm going to use the quotient rule here. And this is a nice opportunity to practice this, remind ourselves of this formula. F prime of x is going to be, okay, what's the quotient rule? Low d high, so e to the x, that's the derivative of the top, minus high d low, so that'll be e to the x times the derivative of e to the x plus 1, which is just e to the x plus 0. I'll just write that as e to the x. Square the bottom and away we go. Okay, I'll simplify a bit. I can distribute this e to the x to those two terms. I can multiply those two together. And I'll get, okay, what's e to the x times e to the x? Well, that's e to the x squared, which is just e to the 2x. And then plus e to the x minus, again, e to the 2x. Over e to the x minus 1 squared. And we get a nice cancellation, right? E to the 2x cancels with negative e to the 2x, and we are just left with e to the x over e to the x minus 1 squared. And that's as simplified as I'll go on that one. Okay, just applying the quotient rule. All these techniques we already know and love. We're just seeing these e to the x's and natural logs pop up now. How about example 6? Find the derivative of f of x equals natural log of e to the 5x plus 3. This is looking like a chain rule to me, which is no big deal. Derivative of the outer around the inner, I'll get 1 over e to the 5x plus 3, and then I have to multiply by the derivative of the inner function. Okay, what's the derivative of e to the 5x? Well, we have another chain rule within there, right? Because it's going to be, okay, derivative of the outer is just e to the 5x, and then derivative of the innermost function, which is 5x, that derivative is just 5. And then plus the derivative of 3, which is 0. So we get this. Okay, so maybe I should add a note. This is a chain rule within another chain rule. Right, because we had that interior function, which we had to use a chain rule for, and yet another interior function to do another chain rule for. All right, but now that we got through that, let's just simplify. I believe we'll just be left with 5 e to the 5x divided by e to the 5x plus 3. And that's as far as we can take it. No common factors or anything like that. We could just leave it in that form. Okay, so I think you could handle the derivatives on the homework and on the review for our upcoming final. Let's look at some integrals now. How about indefinite integral e to the 5x dx? Okay, well, we have a composition, right? And with integration, we don't have the chain rule, what we use as a u substitution. Okay, so seeing as we have a composition here, I might just let u be the inner function that we have here, which is 5x. So then du is equal to 5 dx, and I could solve for dx. Right, so 5x is going to get replaced by u, and then in for dx, I'm going to put du over 5. And that's all we have to do. We don't have a definite integral here, so I don't have to worry about any limits of integration. So we'll have this, the integral of e to the u du over 5. And I might bring that 1/5 on the outside of this integral. So then I just have e to the u du. So this will be 1/5 times e to the u plus c, right? Because the integral of e to the u is just e to the u. And then I can replace u with 5x, so I get 1/5 e to the 5x plus c. You could write it like that, but I can just multiply in that 1/5 like that. I don't need to distribute it to the plus c, because c is just a constant that won't be affected by multiplying by 1/5. And this is what we get. Okay, you could always check your work by taking a derivative using the chain rule and make sure you get back to just e to the 5x. All right, but this gives us a general rule where if we ever have the integral of e to the, I'll just say ax dx, this is just going to be e to the ax over a plus c. So I might not do a u sub every time that we see an integral in this form. I might just refer back to this example. Example 8, and I think, yeah, this is our last page here. Example 8, we want to take the integral of e to the x over 1 plus e to the x dx. All right, can I simplify this expression at all? No, not really. I'm not going to be able to break this up into multiple, the sum of multiple fractions, because we have the addition happening in the denominator. Probably another u sub. I'm just thinking what would I want my u value to be. Maybe just let u be that denominator. So 1 plus e to the x. I'm thinking that this is going to be a good idea because when I take the derivative of both sides, I'll get du equals just e to the x dx, right? So then du over e to the x is equal to dx. And I'm liking the look of this because this is going to become u. I was just hoping that something would cancel with that e to the x, and it looks like I'm going to get that. So making the substitution, this will be the same as the integral of e to the x over u du over e to the x. And sure enough, the e to the x's make a big 1. They go away. This is just the integral of 1 over u du. What's the integral of 1 over u? No power rule here. Remember, this is where we get the natural log of the absolute value of u. Plus c, of course. And I will just substitute in now for u to get it back in terms of x. 1 plus e to the x plus c. Okay. And you could leave it in this form, but actually these absolute values are a redundancy because 1 plus e to the x, this is going to be greater than 1 for all x. Because the graph of e to the x exponential functions look like this, where they have a horizontal asymptote. They never go below, they never touch the x-axis, they never go below the x-axis. So the range of e to the x is the same as the domain of the natural log, which is all positive real numbers. So I actually, just to be, real clean about it, this is the same as the natural log of 1 plus e to the x. I don't need the absolute values because that's always going to be a positive output. So I'll write my answer like this. Good. We've got one more example here. Example 9. Find the equation of the line tangent to the graph of f of x equals 2e to the root x at x equals 4. Okay, just like always with these, our answer is going to be in the form y equals mx plus b. I tend to write this at the beginning of tangent line problems because then the direction is clear. First I want to find the slope m. My penmanship is not very good today. I don't know why. Let's find m. This is just going to be the derivative, so f prime evaluated at our x value, which is 4. Okay. So what is the derivative of f? Well, I think we have a chain rule here. It'll be 2 times the derivative of the outer function around the inner function, which is just e to the root x, and then multiply by the derivative of the inner function, which will be 1 over 2 root x. That will be my chain rule. And of course, we want to evaluate this at x equals 4. I'll simplify a little bit first. I think I just am left with e to the root x divided by root x because the 2 in the numerator and the 2 in the denominator cancel out. So now I want to evaluate this at x equals 4. And that will give me e squared over 2. Like that. And I'm not going to put this into my calculator. I'm just going to leave it in this form, and that is my slope m. Now from here, I want to find the y-intercept b. You could do this using the point slope formula. You could plug m in and x and the output f of x and solve for b. I think that's what I might do. Before I do that though, I'm going to want to find the ordered pair because I have that. Okay, I'm going to use y equals mx plus b with, okay, m we just found is equal to e squared over 2. And we have the ordered pair for f of 4, which is, so I'm going to want to find what is f of 4. That'll be 2e to the square root of 4, so 2e squared. All right, so I'm going to do a little bit of arithmetic in terms of e here. So we'll just be careful. So let's do it. Let's substitute in these values. Y is 2e squared. This will be equal to e squared over 2, that's m, times b, which is 4. Or times x, which is 4. I think I might have said b here, plus b. Right, so I substituted in for those values and I'm solving for b. Let's simplify a bit. 2e squared is equal to 2e squared plus b. Subtracting 2e squared from both sides. B is equal to 0. That's kind of nice. So now finally, my equation will be y equals mx plus b, where m is e squared over 2x plus b, which is 0. So this is it. That is my equation for the line tangent to the graph of f of x equals 2e to the root x at x equals 4. So I'll box that up and I'm done. And that brings us to the end of 6.1. So we're just getting used to working with e to the x, natural log of x, logarithms. In the next section, we are going to see a great application where we're going to use an integral that has, the base Euler's number. It's going to involve annuity and future value of income streams. We'll be able to track the value of investments. This is a very, very helpful, potentially life-changing section, actually, if you follow some of the advice that we discover in these examples. So I'll see you in the next video, 6.2.